let me just, I gotta have some distance from the students, or to protect myself mainly. Be worried in case they attack. It could happen at any moment. Yeah, yeah, right. You gotta just make sure to keep your distance. Don't take your eyes off the student and back away slowly. That's, well, no, no, well, let me just change it. Well, looks like we're going with blue here then. I mean that. Uh, uh, how am I doing on time here? I got 1 minute to go. Well, I think it's about time to start. Just a reminder, we have a course page. There we go. Let's hop on Moodle. There we are. There we go. So there's nothing due today, in case you were worried. There's no homework due today. It just didn't quite feel right, to give you a homework, immediately after break. Uh, especially since we had an exam recently. So you'll find homework here. Don't forget that there is a project up here, but don't forget about that. It's just a PDF document, so it doesn't show up on as an assignment. But the basic idea is, again, there's a turtle sanctuary, and there are two plans for a highway, and the issue is we want to figure out which highway stays furthest away from the traumatized turtles. Right? Yeah. Jackson hasn't heard this one. No. Okay. Yeah. You're just kind of like, what is this? Look, I get bored in my office. So you can read the letter at your own leisure. Okay. But I just want to kind of briefly remind that this is a project where you don't have to do it by yourself. You can work in, what do I say exactly? I think in groups of 2 or 3, but you type a single report, and you even type the math, which at first may feel impossible to you. But I included links here. Dang it, they changed the page. 404 not found. Where'd it go, Microsoft? I bet you Google Docs doesn't change theirs. Okay, yeah. Describes how to type in equations. If you're using OneNote, one of the great things about OneNote is if I'm like, oh, I want to write this, I want to take the derivative of x cubed over cosine x, right? Something like that. Okay. One of the things I can do on OneNote, and I have to go to this draw menu and go to math. I can do ink to math, and it will convert it really nicely for me into some text. You can tell it did a pretty good job there. So I can insert that in, and then I can go to Word, and you can actually just copy and paste it in there. There we go. Oh, Never mind. There we go. No, never mind. Well, they've changed it. It used to do this automatically. Here, I think I have to go to this. Yeah, make sure you select that paste right there. Did you know that there's different types of paste you can do on Word? When you paste in, you can be like, oh, this one, which is basically the default right there. Right there. All those things. Okay. Just want to show you that. All right. Any Connor has a bionic arm now. Well, looks so cool. By the way, speaking of bionic things, be sure to check out the Houghton Star on Friday. Okay. Houghton Star is our student newspaper. It's going to be interesting. So just a reminder, what we were doing, I figure we'll start off today by just reviewing some of these problems here. I'm not even going to do part D. Let's do part E together. Let's do part E. We were doing U substitution. And as you may recall, the idea behind U substitution is you let your U be something that, well, is difficult to work with. That, if it's sort of, it's oftentimes the inside of something in parentheses. And the idea is that by letting U equal this complicated expression, you can sometimes have an integral go from being incomprehensible to actually fairly understandable. I don't know if anyone got started on this, but looking at this right here, it may not be immediately clear what your U ought to be. I don't know. Does anyone want to suggest what we should try for a U here? Yeah, you could try U with the square root sine x plus 9, but actually the square root is just going to make things worse. You're welcome to try it. But what's inside the square root though? That's a good idea for letting that be your U. There's kind of this art form to picking out what the correct U is, and you get better at it by practicing this and picking the wrong ones. And after a while, you're like, oh, yeah, that one does not work. So it's really kind of one of these things you have to learn from experience on how to do it. So we'll be sure to do more practice of these throughout the rest of the semester. So I'm just telling you that's our U, and then our next step is to take the derivative of U with respect to x. The derivative of U of sine is cosine. And the thing to notice is that we get this cosine x dx right there. It matches exactly with our integral. And so when we do this integral, what will we have? Well, that whole blue part can just be du, and that denominator can just be square root of u, which is nice. All right, now the question becomes, what are my bounds here? There's a couple different ways you could do this. You could just do the indefinite integral first, but are my bounds going to be pi over 2 here? I was like, is that one going to be pi over 2, or do I have to change it? You're like, Brandon, wasn't this a week ago you talked about this? Do you expect me to remember everything? Well, there's two different ways. One where you do the indefinite integral, and the other where you just do a different definite integral. And the key is to plug in your bounds into your u function. And so looking at this u function here, if I were to plug pi over 2 into it, that would be sine of pi over 2. Does anyone know what sine of pi over 2 is? It's 1, yes, correct, 10. 1 plus 9 is 10. And then when I do this one, it will be sine of negative pi over 2 plus 9. Sine of negative pi over 2 is -1, so I'll get an 8. And so I can just get it down to this integral here. This is pretty nice looking, I think. That's the idea there. So just to kind of recap briefly, this method, I kind of showed two methods for part A, how to do them. One of them was using this indefinite integral approach. And then, I figure out what the indefinite integral this is. I get it's -1/2 cosine x squared plus a constant after I do my u substitution, and then I plug into this without the plus c to get the answer. And then the other approach to part A, I do here where I change the bounds from 0 to pi to u of 0 to u of pi. So if you're looking for a reference for how to solve the same problem two different ways, take a look at that. That's why they're both part A there. Now, any ideas on how to do this integral? I mean, that square root of u in the denominator doesn't look much better. Yeah, u to the -1/2, that's the way to go, right? So we'll do u to the -1/2 du 10 to 8. And what's the antiderivative of u to the -1/2? Yeah, 2u to the 1/2, right? And we have to plug in at 10 to 8. So you'll get 2 times 10 to the 1/2 minus 2 times 8 to the 1/2. And when we do that, what do we end up getting? Really got to fix this table. This is ridiculous. 0.6677 about. There's got to be a way to stop this. There. Nope. Okay. So any questions on this? This is u substitution. Yeah, Lee. I don't prefer. I have no preference. You can do whatever you feel most comfortable with. So if you like the first method where you just do the indefinite integral and then plug in, that's fine with me. I don't care. Okay. So we're starting to near the end of the course. Did you know that? Things are coming to a close. We have only a few more topics left. And I forgot to upload a slide here. Oh wait, there's something. Chat. If we do both messes, do we get extra credit? No, sorry. No, yeah, just one of them. It's a great way to check though. Great way to check your work. But yeah, here are my two topics that I have officially left. I'll find something else to do. Don't worry. Make sure you review. I'll try to get you a running start for your next math or physics class. All right, so the next topic we're going to discuss is called the natural logarithm. And so let me share this with everyone. So you've learned about a lot of different functions. You've learned about, the trig functions, for instance, sine, cosine, tangent, cotangent, secant, cosecant. But there are more functions in the world than we have really covered. Did I forget to turn on? No, this earpiece. I thought I forgot to turn on the earpiece for a second, but now it's on. And so today we're going to learn a new function. You may have seen it before. You may have seen this if you had a certain type of pre-calculus class before this one, but I don't expect you to have seen it. And so here's the problem that sort of shows why we need another function in mathematics besides just the ones we already know. Um, let's suppose I were to ask you to take the antiderivative of 1 over x. Well, that's the same as x to the negative 1, right? And so you might think to yourself, okay, that's no problem. I have this great formula for how to take antiderivatives of x to n's. It's just x to the n plus 1 over n plus 1, and I just have to remember to add a c. And so you think to yourself, okay, well, I just got to plug in n equals negative 1 into this equation. And so you go ahead and do that, right? So you plug n equals negative 1 here, plug n equals negative 1 there. Well, this thing will simplify to x to the 0. The denominator will simplify to 0. And well, in the end, you get 1 over 0 plus c. And so you get your calculator out and you're like, what is 1 divided by 0 anyways? And you type it in and you get an error. Turns out you're not allowed to divide by 0. It's undefined. Grr. Okay, well, what do you do now? Because sometimes you need an antiderivative for 1 over x. How do you make an antiderivative for 1 over x? And the answer is we're going to define a new function. We are going to define, this is an L and an N here. It's called ln of x, or the natural logarithm. Or if you're French, logarithm naturel. Okay, whichever one you prefer most. So this is a function called the natural logarithm. You may have learned about logarithms in other classes. This will be related to those, but it's not obvious yet why. And what this function is it's basically a function that says, okay, you've got a value of x, I don't know, maybe x is 3. All right, go ahead and do the integral from 1 to x, or in this example, 1 to 3 of 1 over t dt. You'll get a number, bam, that's the value. And so the natural logarithm of x has this property that it's defined using this integral. Now, this should remind you of area functions. Remember area functions from earlier? Those were when we were talking about the second part of the fundamental theorem of calculus. We would have these functions a of x that would be, some value c to x of f of t dt. And we discussed how to take the derivative of those. Does anyone remember what's, in this context, what is the derivative of a? It's just f of x, right? This is ftc2. And so when we look at this natural logarithm function and we take its derivative, one of the things we'll find is that we can use that fundamental theorem of calculus part 2. The derivative of this area function is just the function that we were integrating in the first place. And so for this problem, the derivative of ln of x is 1 over x. This should feel like cheating a little bit, because it kind of is. We've basically defined a function using an integral, and then using ftc2. This follows by ftc2. We are able to magically get this function to have a derivative that's equal to 1 over x, which is great. Now, I plotted both ln of x and 1 over x here so we could sort of have a visual representation of what's happening. Like I said, this is an area function. And the idea is that the y-coordinate, say at this point, of ln of x is simply the area shaded underneath 1 over x from 1 to the x coordinate. And so the natural logarithm has this nice representation as the area under a curve. So we'll get more familiar with this as time goes by. Another thing about natural logarithm is that it is a continuous increasing function. I'll explain what one-to-one means in just a moment. Let's plot it just to see what it looks like. Here's ln of x. one of the things you'll notice is it's not defined for any negative values of x. It's only defined at positive values of x. And it's one of these functions that when you first look at it, you may wonder if it has a horizontal asymptote because it increases. You could see that it goes from smaller, and it has a nice little increasing path there, but you may wonder, well, does it ever level off? And we can try going out and you may think, oh yeah, it definitely looks like it's leveling off a little bit. Maybe it levels off at 4. But if you go a little bit further, you're like, no, nope, it didn't level off at 4, did it? It crossed it. Well, maybe it levels off at around 5, you might wonder. Or yeah, so you might wonder, does it level off at 5? And you're like, oh, maybe, no, it doesn't level off at 5. And then you may be wondering, well, does it level off at 10? Uh-oh, something got resized there. Does it level off at 10? And you're like, well, surely it'll level off at 10. Oh man, this touchscreen is not doing me any favors today, huh? And you're like, geez, how far do I have to go before it gets past 10? But bam, it will eventually. And so it takes a really long time for it to reach values. Like it takes, you got to plug in this massive about 22,660 before you finally get an output of 10, but you will get an output of 10. And you can do this for any number. You can pick a number like, I don't know, say 1 billion. There's going to be some x value where natural logarithm hits 1 billion. What is it exactly? Well, it's a huge number, huge input number, but there is something that it'll reach to. The natural logarithm is it is continuous increasing, and the range of the function, that is the set of possible outputs, the outputs of this function can be anything from negative infinity to positive infinity, anything at all. I've sort of showed you here on this graph that it can get pretty much as big as we want. At least it could get it up to 10 eventually. How about being negative though? Well, being negative is a little bit easier to see because you can see that as we go from 1 towards 0, it plunges really fast and it just keeps plunging. You think it can't get any lower, but it does. It just goes down really low like that. And so the natural logarithm can take on any value between negative infinity to infinity. And the last term I want to mention here is this term called 1-to-1. And 1-to-1, this is a concept you'll encounter more in Calc 2 if you choose to take that course. But basically, at one point in calculus, you learned something called the vertical line test. Remember this idea that, let's draw a picture. I just realized I couldn't draw on Desmos. I don't know if you remember this really early on in the semester last year, but I'd give you like circles and ellipses and ask you, oh, is this the plot of a function? And you would say, no, it's not, because it does not pass the vertical line test. So this is not a function. Does not pass vertical line test. Well, what about functions and horizontal line tests? Do functions have to satisfy the horizontal line test? And what's the horizontal line test, you ask? I'm glad you asked. Here, let's pick a different color here. Yeah, red. Like imagine I have this function. Now let's make it a little bit curvier. There. If I were to, say, draw a horizontal line here, right, we could see that it only hits at one point. So at first glance, it appears to every horizontal line only hits at one point. But if I were to do this one here, you could see that it hits at a lot of points. Now, this is still a plot of a function. This is a function, but does not pass the horizontal line test. So we can see that it is a function, no doubt about it, but it does not pass the horizontal line test. And so sometimes we want to give a special name to functions that do pass the horizontal line test. We want to say, hey, is there a special name for functions that whenever I draw a horizontal line, it only hits at one point? And there is. It's called one-to-one. So a function is one-to-one is one-to-one if it always passes the horizontal line test. There we go. And so, for instance, let me draw a function that is one-to-one. Maybe something like that. I defy you. Find a line, any line you want, where it crosses more than once. I purposely rigged it so that it'll only hit at one point at each place. So this is a one-to-one function. And the natural logarithm is similar to it. It's one-to-one as well. If we take a look at the plot of it once more, you can see that if I were to pick, I don't know, say, excuse me for a moment as I adjust that. There we go. There's my line. If I move my line up and down here, you can see that it's only hitting my function at one point each time. So that's all that theorem is really saying. It's saying that this is a one-to-one function. That'll be important later. Another way to think about one-to-one is each input gives a unique output. So in the United States, for instance, if you're a US citizen, an example of a one-to-one function is your social security number. You are a US citizen, and hopefully there's only one person with your social security number, and that's you. So social security numbers are like a one-to-one function. If you have someone's social security number, it doesn't belong to multiple people. It can only belong to one, a one-to-one. Birth dates are a little different though, right? Multiple people can have the same birth date. You can't figure out someone uniquely. If someone says, "Who are you?" I say October 6th. Well, that doesn't really help clarify matters. So birthdays are not one-to-one. All right. Now the natural logarithm is an unusual function. It has some mighty strange properties. And it'd be good to justify why these properties are true. But I'm not going to do that for now. One of the most interesting properties of natural logarithm is that the natural logarithm of 1 is always 0. It's just 0. And we could see that from our plot easily enough. I mean, if there it is. Plug in x coordinate of 1, y coordinate of 0. Input's 1, output is 0. So that makes sense. But this next property is really surprising. It says that the natural log of a times b is the same as the natural log of a plus the natural log of b. Isn't that amazing? I mean, if you're me, it's amazing. So like, for instance, I'll just make up a random number here. There we go. Two random numbers, a and b. I can ask Desmos, what is natural log of a times b? It says it's 2.92888. And if I do natural log of a plus natural log of b, by golly, I get the exact same answer. Isn't that remarkable? Same answer. Not all functions are like this. Don't be mistaken, young people. This is only true for the natural logarithm. Well, as far as you know, it's only true for that so far. It's not true for sine. Like you can't say sine of a times b is equal to sine of a plus sine of b. That's not true. But it's true here, no matter how, you can see as I change my values of a and b, this is always the case. So this is a really important property. Natural log of a times b is natural log of a plus b. Let's skip over to part D. We'll get to part C eventually, don't worry. This says that if you want to take the natural log of a divided by b, It's the same as the natural log of A minus the natural log of B. And so if I did A divided by B here, and I switch this plus to a minus, you can see that, again, I get the exact same values. The natural log of A divided by B is the same as the natural log of A minus natural log of A minus natural log of B. So this too is a wonderful property. You should be thinking to yourself that natural logarithm does something weird to multiplication. It's like here I am multiplying A and B, and then here I'm adding things. It's like it converts multiplication into addition, and it converts division into subtraction. It's kind of a weird function when you first encounter it. Okay, the last of these identities that we should mention is this one, that the natural log of A to the C is C times natural log of A, as long as C is a real number. And so let me, maybe instead of A to the C, I'll do A to the B here. Again, you can see that it doesn't really matter what my A and B are. I'm able to get the exact same value for both of them. So one of the things we can do with natural logarithm is we can use it to sort of rewrite some kind of complicated looking expressions. And I want to make sure we understand these properties. So I have kind of a toy problem, as we call them, toy example. It's not like a real math problem, but it should make it clear what's sort of happening here conceptually. So I'm going to just take a picture of, well, I'm going to attempt to take a picture of these. No, let's try again. One more try here. Notice, by golly, computer, what's going on? Oh, I gotta reselect rectangle. I changed the setting. That's what happened. So I'll keep these laws here so we can see them, but let me show a little toy example of what these laws can accomplish for you, even though it's not particularly interesting, I'll admit, but it's useful for understanding the rules. Imagine we had the following horrific looking expression. Somebody said to you, here, I have this ugly expression here. Could you simplify it for me? Of course, what does simplify really mean? That's hard to say. But imagine you were given that. Look at that thing. Is that a... Yeah, right. So the idea here is I want to use my rules to make this look a little less horrifying, though, you know, kind of the truth of the matter is there's very little we can do about the horrifying nature of this. It just does what it is. But yeah, Megan's comment's spot on here. She said, oh, this is like your A and this is like your C, right? In part C, right here. And so we can write this as 5 times natural log of x squared plus 3 cubed over x cubed plus 4x plus 3. All right, what's the next law we could use to change the appearance of this? I'm going to leave the top portion as is because it's actually not so easy to simplify it. But now I have natural log of something else. Yeah, D. I have natural log of a fraction. So this tells me that this is the same as natural log of my numerator minus natural log of my denominator. So this was using law C. This is using law D. All right. Any other laws we could use here? Is there a law that lets us deal with this? Yeah, there's nothing we could do when there are pluses inside the parentheses for a natural logarithm. There's no rule here that has pluses on the left. So this one is, we're done. There's nothing we can do to simplify that expression. How about this one? Is there any rule we could use here? Yeah, we could use law B. This is an A, and this is our B. So yeah, we could use that law B. And so this will be natural log of X plus natural log of X squared plus 3 cubed minus natural log of X cubed plus 4X plus 3. So this is my natural log of A plus my natural log of B. And that's using, and what's one more? I can, yeah, and then I can use C again, rule C. This is an A, this is a C. And so in the end, we took a terrifying looking expression and made a different terrifying looking expression. This is what we call progress. Now, actually, natural logarithm, this expression here at the end is a bit nicer for some computational reasons. One is that division in general is a terrible operation to perform. Division is never any fun. Multiplication is difficult too. Addition and subtraction, those are nice. What natural logarithm allows you to do is to convert complicated multiplications into additions. And if you grew up before the era of calculators, there was a device that you would use to do multiplication with numbers. I don't know if any of you have seen one of these before, but it's called a slide rule. Slide, it's this little calculator, and it's a mechanical type calculator. You would sort of set up, you would move these little strips of the ruler to multiply your numbers together. If you're like, oh, I need to do, you know, 1083 times 4064, you'd kind of try to line up things just right for about those numbers, and then you look somewhere else and it would tell you the product. So this is what people had to use back in the dark ages. My parents used these when they did math. They were like, yeah. I once got a look at my dad's college transcript. It was not good, my friends. It was not good. He's since passed away, but he was one of those people. Yeah, there's this saying that C students rule the world. That like when you look at who's in charge of the big companies and industry, they're the people who got C's in college. Have you ever heard that? It's true, right? Or even worse, they just dropped out. They're just like, I'm done with college. I'm ready to become a billionaire now. So there's a lot of examples. My dad was a Steve student who ruled the world. At least a construction company. He ruled a construction company. And he had to take computer programming. I don't know why, but he failed Fortran twice and somehow got a D on like the third try. Terrible programmer. So I didn't get it from him. We know that for sure. Genetically, it did not come from my father's side. Anyways, didn't mean to get too off topic there, just a little bit. Okay. So one of the most interesting things about the natural logarithm is taking derivatives involving the natural logarithm. It's pretty cool. And this theorem here really isn't anything special. It's just a version of the chain rule. It says that if you are going to take the derivative of ln of u, well, on one hand, right, we know what the derivative of natural log of x is. We did that earlier, right? We said the derivative of natural log of x is just 1 over x. So if you were to take the derivative of natural log of u, it would just be, 1 over u, but then you have to multiply by the inside, which is u, so you have to multiply by u prime. So this is just the chain rule. It looks like it's something more sophisticated, but it isn't. It's just the chain rule, but it's a nice thing to remember. So if you ever have to take the derivative of natural log of something, it's just, take the derivative of the thing on the inside and then put the original thing back underneath it. So let's do an example to illustrate this. And I'm bringing my drill and fixing this table. I can't take it. I know, I'm going to do it this time though. I just got to get the gumption up to actually do it. All right, so imagine you were asked, take the derivative of natural log of 3x squared plus 2x plus 1. Well, what would that be? Well, you just identify this thing here as your u. And what's your u prime going to be? Well, well, it'd be 6x plus 2, right? That's my u prime. This is my u. That's it. All done. I don't know. Did you like that? It's not that bad. Not that bad in the grand scheme of things. Let's keep that example near us here as we move on to some practice problems. Yeah. I want you to take me some derivatives. And just so we're clear, in order for you to do that, at least for parts A and B and C, you should use these rules first. Otherwise, it gets really hard. So go ahead and try taking some derivatives. They're in order of increasing complexity. My wife and I don't agree on certain things. And one of them is, do you need to purchase travel insurance? I say no. I live life on the wild side. Just got an email. Apparently, she purchased travel insurance for our summer vacation. Oh well, looks like I lost that one. You know how that goes, right? How's it going? That thing's got to cost a fortune. You didn't have to buy it though, right? You just give it back. You have to keep it? Save it for Halloween. Thanks. Don't mind me, Maxwell. I'm just spying on you. You did it correctly. Congratulations. I highly recommend not using the quotient rule in part B. You can do B without the quotient rule. And by the quotient rule, I mean the, uh, low derivative high minus high derivative low over low squared. You should use one of these laws here. To simplify it, then take the derivative. Online students, feel free to ask questions. Oh my goodness, is it really 12:43? I must have just been talking forever. You're such long-suffering students. Such long-suffering students. And I figured out that Keaton and Jackson actually know each other. Right, good. Feel free to work to, and Liz, you can become Jackson's friend too, and or Lee's or Jerry's. They're all friendly. The rest of the class, though, forget about it. I'm just no, I'm not friendly either. Well, I just gotta, yeah. Um, Not quite. So it will be a one, but then you got to put the original thing underneath. So it'll be one over x plus two. Yeah. How's it going, Keelan? Oh yeah, you did it. Good job. Perfect. Guys, excited for the eclipse? When is that? April 8th. Is that on Monday? All right. I wonder when it's gonna be. I'll look that up. Hopefully it doesn't enter 3:36. Okay, good. We don't have to cancel class. In case you don't know, do not stare at an eclipse. It'll be the last thing you ever see. Well, actually, you may, in reality, you'll just end up seeing it for the rest of your life in all likelihood. Yeah, you won't have, you'll be kind of blind in front, but you'll still have your peripheral vision. Look at it with your peripheral. You can get in all sorts of car accidents. Who knows? How's it going, Zachary and Josh? Oh, that looks great. Though it should be an x plus one in the denominator and an x squared plus three.
Because of rule A, you would get rid of that.
No, it's you have this correctly. What you should be thinking of is that rule. It's u prime
okay.
over u. And how goes it? Well, you got part A going well. Yeah, and so the rule you want to use here at this point to take the so you haven't taken the derivative yet. You've just taken it and rewritten the ln of x plus 1 over x squared plus 3 in a different form. So now you got to take the derivative of this. And so you'll use like this will be your x plus 1 will be u here, and so you'll get a u prime over u, and then you'll do it again there. Yeah, that one, yeah, you do have to use the quotient rule on that one. I was wanting to see if I could trick anyone, but you asked. Foiled. But good luck with part E and F. Well, E you could probably do. F is just mean. X plus 1.
Okay, wait. So
it'll be, for this term, it'll be 1 over x plus 1.
okay. That's
Yeah. I didn't mean to throw you off there. Sorry. And then it's minus the 2x over x squared plus 3.
okay.
Well, let's see how's it going, April? The problem is I'm terrible at reading people's work upside down, but I'll try to figure it. I think you did it right. Good job. Good job. You'd think I'd be good at that, but I'm not. Oh yeah, isn't that beautiful? That's it. That's it. That's all there is to it, unfortunately. Yeah, yeah, you're this one you have to use the quotient rule on, yeah.
Do you do, like, use this for that?
Just start by doing the quotient rule and then you'll see what happens. So I'll try to, so many rules. There we go. So I've got, of course, this one from earlier. There's that rule. Then there's good old American quotient rule. Okay, it's not American. The truth is, there's almost no significant mathematics of American significance until the 1920s. Like that's how long it took. Um, so there's a theorem which you'll never learn about. Well, except now you are. The Mordell-Weil theorem, the theorem on Diophantine equation, and it was proposed by Henri Poincaré, who's like one of the greatest mathematicians of his generation, and proved by Louis Mordell, who was the first American-born mathematician to do like something serious. It was like, yes, we've arrived. We all started chanting USA, USA. This is incredibly difficult. I had to learn this theorem for an oral exam, and it was like basically I had to be able to explain how to prove it, but it goes hundreds of pages. It's just insane. When I was first testing out Chat GPT, it was one of the first questions I asked it. I said, sketch the proof of the Mordell-Weil theorem, and it screwed it up royally. Didn't even come close. Modern encryption systems sort of depend on that theorem.
Yes.
Yeah, very good. And that's all there is to that one. And now evil part F. Yeah, maybe I should start going over some of these here. Seeing that most of you have gotten through A, B, and C, so I'm not going to bother writing those ones out. But for D, E, and F, these get pretty ugly pretty fast. So for D, we have to use the quotient rule, which I have written down here. It's the V U prime minus U V prime over V squared. And so in this context, my U is the natural log of X plus 1. And my V is the X squared. So if I'm using the quotient rule here, I'll have X squared. And then I'll have to take the derivative of my numerator. I don't want to think about that right now. It's too complicated. So I just write down this, which is basically code for, let's think about that later. All right. Low minus the derivative of high minus high, and the derivative of low, all over X squared squared. All right, so now the question is, what's the derivative of the natural log of X plus 1? Does anyone know what the derivative of that is? 1 in the numerator, right? And then in the denominator, yeah, you get an X plus 1. And you might be thinking to yourself, do I have to simplify this? Nope. See, this is one of the peculiarities of college mathematics. In high school, they're always like, simplify to this particular form, please. And here, I'm fine with it just being the way it is. All right, that x squared, that's awkward. That's x to the fourth. Okay. So that's that one. Now, how, anyone have any ideas on how we approach part E? Yeah, the product rule makes sense. So I'll do the derivative of x, which is 1, times natural log of x, plus x times, well, what's the derivative of ln of x? 1 over x. So this simplifies a lot. Just ln of x plus 1. That's not so bad. Oh, yeah. So are you saying, hey, there seems to be a rule for for logarithms that applies here? Great, great comment. So Liz says, and she is correct, that x times natural log of x, can't we use that rule, that part C rule here? Yeah, we can. Liz says, this is the same as natural log of x to the x. Excellent observation, Liz. Yes. And so, thus, we haven't just figured out the derivative of x times natural log x. We figured out the derivative of the natural log of x to the x, which is this. It's good thinking, Liz. You just accidentally figured that, yeah. Right. If you were thinking, wouldn't it be easier to take the derivative of this thing? The answer is no way. No way, Jose. This would be really hard to take this one's actually easier. Yeah. But that does sort of bring us to something interesting, doesn't it? Because the next problem is find the derivative of x to the x. Now you may be thinking to yourself, oh, well, can't I just use this rule we did earlier? You know, this x to the derivative of this is right. That can we just use that? And the answer is no, is not applicable. The reason why it's not applicable is that this rule assumes n is a constant. And so if we have x to the x, the problem is, well, x is not a constant. And so we can't do part F using this very basic rule. Wouldn't that be nice? But it doesn't work. It doesn't work. So what do we do instead? Well, we follow from Liz's insight. Liz says the derivative of natural log of x to the x is this. By golly, we're really close, aren't we? If we could just get rid of that natural log, we'd be in business. But we can't. But we also sort of can. So let me explain how. This one is a magic trick. By the way, this particular problem, if you want to become like, say, a mechanical or electrical engineer, this is a job interview type question. You like walk into your first job and they'll say, oh, that's great. What's the derivative of x to the x? And they just want to see, can you not use this rule? They just you may not even have to solve it. You just have to convince them that you're not going to accidentally use this rule. Okay. So that's why I cover it for anyone who wants to become an engineer someday. So here's the thing to recall, that when we take the derivative of natural log of u, right, that's u prime over u. But that also means that u prime is equal to u times the derivative of natural log of u. I just multiplied by u on both sides. Does that make sense? And so here's the idea. Let u be x to the x. Then when we take the derivative of x to the x, we're basically computing u prime. And that's going to be u times the derivative of natural log of u, which in our case, right, what is this really? This is x to the x times the derivative of natural log x to the x. And it'd be nice if we knew the derivative of natural log x to the x. Does anyone know how to take the derivative of natural log x to the x? Yes, Liz does. The derivative of natural log x to the x is that thing. X to the x times natural log of x plus 1. That's the answer for part F. Isn't that a crazy way to do a derivative? There's a special name for this technique. It's called logarithmic differentiation. And good news, I don't make you learn it very much. But it's good to at least be aware of it, that this is a method for finding a derivative. Because sometimes, in very bizarre circumstances, like when you're dealing with x to the x or something like that, it's easier to take the derivative of the logarithm of the function than to take the derivative of the function. That's a kind of weird thought, isn't it? So it's like, oh man, the derivative of x to the x, that's too hard for me to do. Derivative natural log of x to the x, oh, I can do that. And so, yeah, that's kind of a mean, I should put a little star next to that one, just to give people a heads up. It's kind of mean. All right, any questions on all this? We've got like what? How many minutes? 5 minutes. I'll do an example. We'll end with an example. So I've told you that the derivative of the natural log of u is u prime over u. But something else is true as well, which is a little bit better. A little bit better. See, as I kind of mentioned when I showed you the plot of natural logarithm, right? When we were looking at that plot of natural logarithm, one of the things about it is you can't plug negative numbers in. If you go on Desmos and you say, what's natural log of -1, it'll say, beats me. Nobody ever told me what that is. By the way, if you decide to become a math major and take complex variables with me, we'll actually define natural log of -1, but Desmos doesn't know that stuff. It's not that smart. But for us, we're just gonna say it's not defined. So that means that if your u is taking on negative values, this rule doesn't work. This is really only for u greater than 0. So what do you do if your u is negative? Well, here's the idea. You can't necessarily take the derivative of natural log of u in that case if u is negative, but you can take the derivative of natural log of absolute value of u. The absolute value can take any negative number and, well, now it's positive. And unbelievably, this is incredible, but the derivative of natural log with the absolute value of u gives you the exact same answer. It's weird to sort of see why. I used to try to explain this to people, and then I realized that when I tried to explain it to people, I just made things worse. But the basic idea is that if u is taking on negative values, and you're imagining, u is some sort of function that if u is less than 0, then v equal to negative u is bigger than 0, right? And then that means the absolute value of u is the same as the absolute value of v, which is actually really the same as v. And then you can, all right, see, I've fallen into my trap. I'm explaining it now. All right, and then the derivative of natural log of absolute value of u, right? I gotta pretty this up. Hold on, everyone. Let's fix this. All right, this is how I'm not gonna do an example. I'm gonna go on a little rabbit trail here. If u is less than 0, then so if u is taking on values that are negative, let v be the negative of that. And then it follows that the absolute value of u is the exact same thing as v, right? And then when I say, oh, what's the derivative of the absolute value of u? Well, that's the same as asking what's the derivative of natural log of v? And well, we know what that is. That's v prime over v. And well, what is v? Well, v is negative u. So this would be negative u prime over, well, negative u, and the negatives cancel out. Bam. Okay, so that's why the absolute value works. I think this is really cool. Now, the upshot of it is that we're now going to do integrals where absolute values start popping into existence. So absolute value isn't just one of those weird things you learn just for the fun of it. It turns out to be really important. And you may think this is crazy, but eventually we're going to see that. Well, have you noticed that I've taught you the antiderivatives of sine and cosine, but I haven't taught you the antiderivative of tangent? How do I take the antiderivative of tangent? That's a good question. See if you could figure it out. That's a good question. This talk about natural logarithms will help. Okay, that's it for today. I'll see you folks later. Any questions, online students? Nope, you're all set. Okay, all right. I'll see you later. Email me if you do have them. Bye.